does a monopoly look like in the 21st century? Forget the old antitrust cases. Today, it might look like Nvidia's latest quarterly earnings, a staggering $39 billion from their core data center business. To put that in perspective, that's not just more than their biggest rival, AMD, made in the same segment, it's over 10 times more. It's an economic conquest and a near total capture of the AI infrastructure before it's even begun yet. But the real story here isn't just their balance sheet. It's the sheer scale of the gold rush they're supplying. We are in the middle of a spending spree of historic proportions. McKinsey predicts a $7 trillion infrastructure investment is needed by 2030 just to keep pace. OpenAI is planning a data center codenamed Stargate with a $500 billion price tag. The name is fitting, the numbers feel like science fiction, and here's the critical bottleneck that defines our entire era. For now, all of that historic spending, all of that ambition, has to funnel through a single company. And that bottleneck is Nvidia. It's how a single company ends up with a 92% market share for the AI chips powering this revolution. Let's be clear, that isn't a market share. It's a rounding error away from a monopoly. It's why for the last few years, the world's largest and most powerful companies have been happy to line up and pay whatever it costs to get into Nvidia's exclusive party. But here's the thing about a party this good and this expensive. Eventually, someone tries to sneak in through the back. Or, more accurately, they try to build their own, cheaper party next door. A quiet, multi-front challenge is now taking shape. So the question is, can anyone actually challenge Nvidia? Let's unpack this. To understand the scale of the challenge, you have to appreciate the fortress Nvidia has built. It's not just about having the fastest chip. The real moat has two very deep and brilliant layers. The first layer isn't hardware, it's software. To understand it, we first need to understand what a GPU, or graphics processing unit, actually is. Originally designed to render graphics for video games, GPUs are built differently from a computer's main processor. Instead of a few very smart cores, they have thousands of simpler cores that can all work at the same time. This is called parallel processing, and it turns out this architecture is a perfect match for the mathematical models behind AI. But there was a problem. How do you tell all those thousands of cores what to do? You need a common language. And this is where Nvidia played its masterstroke with CUDA. Think of it like this. CUDA became the English language of AI computing. While other powerful languages exist, like AMD's ROCm or the Universal Translator OpenCL, Nvidia made CUDA so accessible and supported it so well that it became the global standard. Almost every major AI breakthrough was written in CUDA first. So to compete, rivals don't just need a powerful chip. They need to convince an entire world of developers to become fluent in a new language. And CUDA is more than just a language. You can think of a GPU as an assembly line with thousands of robotic arms ready to perform tasks in parallel. CUDA gives users the key to the control panel for the assembly line. They aren't just selecting from a menu, they are programming the exact speed, torque, and angle of every single arm, designing a custom assembly line perfectly optimized for their AI model. For 20 years, Nvidia gave the CUDA toolkit away to universities and researchers, creating a lock-in based on human capital. The simple fact is, the best AI researchers in the world, the people companies are paying 7-figure signing bonuses to hire, grew up using CUDA. It's their native language. It's what they're comfortable and productive with. Asking this scarce, incredibly expensive talent to switch to a different, less mature toolkit is a non-starter. You don't hand your star Formula One drivers a wrench from a different team and tell them to figure it out. You build the car around the drivers. And right now, the drivers demand Nvidia. That is the genius of their software moat. But that software moat is reinforced by a hardware moat. Nvidia understood that the most powerful AI models are too big for any single GPU. To train them, you need multiple GPUs working together as a single virtual megachip. This is what Nvidia calls scaling up. The problem is that when you connect multiple GPUs, the connection between them becomes a bottleneck. The chips end up waiting for each other to send and receive data. Nvidia's solution is a piece of hardware called NVLink. Think of it like building a massive Lego spaceship. You need a team of 8 master builders at one table. If they have to get up and walk across the room for every piece, most of their time is spent waiting. NVLink is a private, super-fast conveyor belt system that connects all 8 builders at the table. It delivers a staggering amount of data per second, so the builders never wait. They work as one hyper-efficient unit. But here's the next level of the problem. Training a truly massive AI model, like the one powering ChatGPT, requires more than just 8 builders at one table. You need thousands of these tables, thousands of servers, all working together on the same giant project. This is called scaling out. And this is where most systems break down. Connecting thousands of individual computers or servers with a standard network is too slow. It's like trying to run a city's logistics on narrow country roads. You'd have constant traffic jams. So, in 2019, Nvidia made one of the smartest acquisitions in tech history. They bought Mellanox, the leader in a networking technology called InfiniBand. InfiniBand is essentially a private, high-speed superhighway designed specifically for connecting servers in a supercomputer or data center. By acquiring Mellanox, Nvidia now owned the blueprints for the superhighway. This is what truly enables the AI factory Jensen Huang talks about, a facility where data flows frictionlessly from a single chip to tens of thousands of them. This combination, a locked-in software ecosystem and a vertically integrated hardware system, is the foundation of Nvidia's empire. It's a full-stack solution that is incredibly difficult to replicate. And it's this fortress that a new wave of challengers is now attempting to storm.
In the world of AI, a chip has to do 2 very different jobs. Understanding this difference is the key to the entire competitive landscape. The 2 jobs are training and inference. First, there's AI training. This is the process of teaching the model. You show the model a massive data set, like the entire internet, and it learns patterns, relationships, and concepts. It's the equivalent of cramming every book ever written into a university library all at once. It's a brute force, one-time event that requires tens of thousands of GPUs working in perfect synchrony for months. This is Nvidia's home turf. It's exactly what their scale-up and scale-out systems, like NVLink and InfiniBand, are designed for. For this job, you need the most powerful integrated system money can buy, and right now, that is indisputably Nvidia. Trying to beat Nvidia at training is like trying to outsprint a cheetah. You might be fast, but you're not that fast. It's a battle they've already won. But once the model is taught, the work changes. This brings us to the second battleground, inference. Inference is the process of using the trained model to make a prediction or generate an answer. It's asking ChatGPT a question, translating a sentence, or generating an image. In our analogy, it's the day-to-day work of the library. Every single question asked by every single student. It's using the knowledge that's already been built. And this is where the economics of AI completely flip. As technologist Pete Warden put it, training costs scale with the number of researchers, but inference costs scale with the number of users. Let's break that down. A single training run might cost $100 million, but you only do it once. Inference, on the other hand, might cost a fraction of a cent per query. But when you have a billion users making billions of queries a day, those fractions add up to become the single largest cost for any AI company. And because of this, the way you measure success gets turned on its head. For training, the goal is pure, unadulterated speed. It's a time-to-market race where the only thing that matters is raw horsepower. How quickly can you get your groundbreaking model built and deployed? But for inference, the metric isn't horsepower, it's miles per gallon. The business question becomes, What is your cost per query when you're serving a billion users? Suddenly, that Ferrari of a training chip looks wildly impractical for the daily commute. Here is where total cost of ownership becomes the only number that matters. The sticker price, the energy bill, and raw efficiency are what determine the winner. This is the crack in Nvidia's armor. This is the strategic opening. The challengers aren't trying to beat Nvidia at its own game of building the most powerful training systems. They're trying to build a different kind of system, one that is good enough and dramatically cheaper to run at the massive scale of inference. They are flanking the fortress. Now, let's see who they are. The assault on Nvidia's fortress is coming from three distinct fronts, each with a different strategy. And the most fundamental of these is the software abstraction threat. This isn't a single competition. It's a rival philosophy, a silent coup being staged in the world of code. To understand it, think back to the dawn of the personal computer. For years, if you wanted raw speed, you wrote in hand-tuned assembly language, brutal, low-level code specific to one CPU. But then, high-level languages like C++ emerged, allowing you to write code once and have a smart compiler optimize it for any processor. Flexibility and speed of development won. Assembly language became a niche. CUDA is today's assembly language for AI. It's incredibly powerful, but it chains you to Nvidia's hardware. The software abstraction threat is the C++ moment for AI, a movement to make the hardware underneath irrelevant. But is this just a theory? There is growing evidence that an open-source rebellion is gaining momentum. This rebellion is a two-pronged attack, funded and executed by Nvidia's own biggest customers. At the framework level, you have PyTorch, the world's most popular AI framework, backed by Meta. PyTorch is now at the center of a massive effort to support alternatives to CUDA. Through open-source initiatives like RockM for AMD and OneAPI for Intel, the community is building the software bridges to make other hardware viable. But the rebellion goes deeper. At the kernel level, you have Triton, an open-source language sponsored by OpenAI. It's a direct shot at the heart of CUDA, allowing developers to write high-performance AI code that is not tied to a single hardware platform. Why would Nvidia's biggest customers, Meta and OpenAI, invest billions in these open tools? It's their long-term escape hatch. They are building the software that will allow them and everyone else to one day choose their hardware based on price and performance, not proprietary lock-in. This is the silent code-level rebellion that is trying to drain Nvidia's moat. But a software rebellion is useless without alternative hardware to run on. And that brings us to the second front of this battle. The hyperscalers aren't just sponsoring the rebellion, they are actively building its arsenal. Nvidia's biggest customers, hyperscalers like Google, Amazon, and Meta, have a very simple and very expensive problem. When your single biggest capital expenditure is writing multi-billion-dollar checks to one supplier, you eventually decide to try and build the product yourself. And that's exactly what they're doing. They are pouring billions into designing their own custom AI chips, known as ASICs. ASIC stands for Application-Specific Integrated Circuit. The name says it all. It's a chip designed from the ground up to do one single application or task with maximum efficiency. Think of an Nvidia GPU as a phenomenal, all-purpose Swiss Army knife. It's incredibly versatile. It functions as a blade, a screwdriver, and a bottle opener. A GPU can tackle almost any computational task you throw at it, making it ideal for the rapidly evolving and diverse needs of AI research and development. A custom ASIC, however, is not a Swiss Army knife. It's a dedicated bottle opener. It does one thing, and because of that, it can open bottles faster, cheaper, and with less energy than any other tool on the planet.
Google's TPUs, for instance, are ASICs heavily optimized for the specific mathematical operations used in their AI models. Amazon's Inferentio chip is another, designed for high-performance inference at scale. They aren't trying to build a better all-around chip than Nvidia. They are building a cheaper, more efficient chip for the one job they do billions of times a day. Historically, the main target for these custom chips has been inference. That's the high-volume, cost-sensitive work of running the model. But the rebellion is now spreading from the fringes of inference to training. In June, OpenAI, one of NVIDIA's most important customers, began using Google Cloud Platform to power its products and looking to Google's TPUs for compute. This is the first time OpenAI has meaningfully used non-NVIDIA chips. They are actively diversifying their hardware supply to lower the staggering cost of running services like ChatGPT. And they're not alone. Reports note that Apple and Safe Superintelligence are also turning to Google's TPUs as a viable, cheaper alternative. So how significant is the cost advantage? Here's VentureBeat reporting on Google's TPU cost advantage. Google may be obtaining its AI compute power at roughly 20% of the cost incurred by those purchasing high-end NVIDIA GPUs. While the exact numbers are internal, the implication is a 4x to 6x cost efficiency advantage per unit of compute for Google at the hardware level. This doesn't mean the hyperscalers are abandoning NVIDIA. They are pursuing a sophisticated two-track strategy. They use their own cheaper custom chips for the high-volume commodity work of inference, but for training the next generation of truly groundbreaking models, the task that demands the absolute pinnacle of performance, they are still buying everything NVIDIA can produce. This kind of strategic tension, where companies are both partners and rivals, is one of the most fascinating narratives in tech. It's a theme we break down constantly in our newsletter, ARPU. We won't go deeper into the financials here. If that's your kind of thing, you know where to find the link. Now, while the hyperscalers are fighting to escape a financial prison, the third front is a response to being locked out of the global supply chain entirely. The United States government didn't just impose tariffs, it drew a digital iron curtain around China. The goal was to hit a kill switch on their AI development, cutting them off from the two critical inputs they couldn't make themselves: NVIDIA's top-tier GPUs and the bleeding-edge manufacturing tools from ASML. The strategy was simple. If you can't buy the best shovels, you can't join the gold rush. It was meant to put China's AI ambitions on ice, but it had the exact opposite effect. Necessity, it turns out, is the mother of a state-sponsored monopoly. By locking NVIDIA out of China, the US government inadvertently locked Huawei in. It handed them the keys to a $50 billion competition-free kingdom and a national mandate to conquer it. And Huawei took a page from a different playbook. If you can't build the single most powerful Death Star, build 1,000 nimble starfighters and network them together. Their strategy isn't about winning a one-on-one duel. It's about winning with a perfectly coordinated swarm. This isn't theoretical. Huawei's flagship system is called the Cloud Matrix 384. It's a computing cluster that physically links 384 of their Ascend 910C chips together. This is a scale-out philosophy taken to the extreme. They're using advanced packaging and high-speed optical connections to compensate for the lower power of their individual chips. And the results are startling. A technical paper published in June showed that in a test running the DeepSeek R1 model, Huawei's Cloud Matrix system actually outperformed a comparable system using NVIDIA's H800 chips. Even Jensen Huang admits Huawei is a formidable competitor and that their strategy of stacking and clustering is a viable way to achieve world-class performance. While this system is less power efficient than NVIDIA's, that's a problem China can easily afford. With electricity costs at less than half of those in the US, Huawei can prioritize what matters most, locking down a captive market of the world's largest internet companies with a government mandate to succeed. They are now exporting their entire AI stack to allied nations, creating a completely parallel, non-American technological sphere. So the result of US policy isn't just a competitor, it's the creation of a fundamentally bifurcated world, one that runs on Nvidia and one that will increasingly run on Huawei. This is the new reality of the AI Cold War. This brings us to another question. AMD is still catching up, and Huawei is limited by manufacturing. So how can software giants like Google and Meta realistically mount a challenge in the brutal, specialized world of chip design? The answer is, they don't do it alone. They have a powerful and very quiet partner, a trillion-dollar partner, in fact. That partner is Broadcom. While all eyes have been on Nvidia, Broadcom stock has quietly become one of the best performers in the S&P 500, surging over 60% in the past 12 months and crossing a $1 trillion valuation. And the reason for this meteoric rise is that they are the ultimate arms dealer in the chip wars. Broadcom doesn't build headline-grabbing GPUs to compete with Nvidia directly. Instead, they master all the other critical, high-performance components you need to build a modern data center. And their business model is the polar opposite of Nvidia's. While Nvidia sells a closed, all-in-one system, Broadcom sells best-in-class components to anyone, enabling an open, mix-and-match ecosystem. This is how they fuel the Hyperscaler rebellion. When Google designs a new TPU, they focus on their secret sauce, the core AI logic. For the critical surrounding infrastructure, they turn to Broadcom. Need an industry-leading networking fabric? Broadcom's Tomahawk switches are the main alternative to Nvidia's. Need the packaging technology to fuse a system together? Broadcom provides the blueprints. This is the core of the custom chip market. An industry Morgan Stanley projects will more than double from $12 billion last year to $30 billion by 2027. This entire market, in essence, represents revenue that is being diverted away from Nvidia, enabled by Broadcom's open-door policy. It's why some on Wall Street have started calling them one of the three horsemen of AI, right alongside Nvidia and TSMC. Broadcom gives the hyperscalers a credible, off-the-shelf path to building their own competitive AI systems. They enable an a la carte menu for an industry that has been stuck with Nvidia's expensive, all-inclusive prefix. They don't need to kill the king, they just need to sell enough shovels to the rebels digging tunnels under the castle walls. And if you want to know how seriously Nvidia takes this threat, look no further than their recent announcement to open up their NVLink platform. When they listed their initial partners, they included names like Qualcomm and Marvell. The one name pointedly left off that list? Broadcom. Nvidia knows exactly who is arming their competition, and that forces the king to respond. A $1 trillion empire doesn't sit idle while rivals gather at the gates. Nvidia isn't just defending its position, it's actively expanding its territory. Their response is a counterattack designed to make their ecosystem not just powerful, but completely indispensable. Their first line of defense is relentless innovation. While competitors struggle to match their current chips, Nvidia is already on a punishing one-year release cycle. They moved from the Hopper architecture to the powerful Blackwell platform this year. They have also announced its successor, codenamed Rubin, for 2026. This rapid pace does two things. It widens their performance lead, making it a moving target that rivals can never quite catch. But more importantly, it reinforces the power of their software. Every new hardware generation comes with new features that are only accessible through the CUDA platform, making the cost of not being in their ecosystem even higher.
But Nvidia's grand strategy is bigger than just selling chips. They are repositioning themselves from a component supplier to the architect of the entire AI factory. This is the core of Jensen Huang's vision. They aren't just selling you the robotic arms anymore, they're selling you the entire prefabricated, turnkey factory floor.
In fact, these AI data centers are not data centers at all. They're not data centers in the classical sense of a data center, storing your files that you retrieve. These data centers are not storing our files. It has one job and one job only, to produce intelligent tokens, the generation of AI. These factories of AI look like data centers.
These are their DGX systems, fully integrated racks and pods that combine their CPUs, GPUs, and networking into a single optimized supercomputer. An enterprise doesn't have to worry about integrating parts from 10 different vendors. They just plug it in, and the factory starts producing intelligence. This AI factory model is a great pitch for their newest customer base. Entire countries. The concept of sovereign AI has exploded onto the scene. Nations now view owning their own AI infrastructure as a matter of national security. And they aren't buying individual chips. They are buying national capacity. Nvidia has seized this opportunity, signing deals to build national AI clouds for countries like Saudi Arabia, Germany, and the UAE. This brilliantly expands their business and diversifies it away from the very hyperscalers who are trying to build custom chips. Finally, Nvidia is adapting to the customer rebellion with a classic embrace and extend strategy. This is the NVLink Fusion initiative. For the first time, Nvidia is opening up its proprietary server architecture. It allows partners like Qualcomm and Fujitsu to replace Nvidia's owned CPU with their custom designs, while still using Nvidia's world-beating GPUs and networking fabric. It's a strategic move. It says to the world, go ahead, build your own custom processor, but you'll still need to plug it into our system to get the best performance.
So, we come back to the original question. Can anyone truly challenge Nvidia? The answer isn't a simple yes or no. It's about when. Nvidia's monopoly on raw performance is safe for now, but its iron grip on the entire market is starting to show hairline fractures. To see why, you have to look at the AI supercycle not as a single event, but as a campaign with 4 distinct phases, a playbook laid out by analysts at Goldman Sachs. Phase 1 was the starting gun, selling the hardware, the raw picks and shovels for the gold rush. Nvidia owned this. Phase 2 is where we are now, the great infrastructure build-out. This is the brute force phase of laying the trillion-dollar foundations, the data centers, the cloud services, the training clusters. This is Nvidia's home turf, a game of pure power where they are the undisputed champions. As long as this infrastructure frenzy continues, their position feels unassailable. But here's the plot twist, and it's a big one. The game is about to change. According to the Goldman playbook, we're on the verge of a critical pivot into Phase 3. Phase 3 is where the economic center of gravity shifts from building AI to using AI. It's about monetizing AI in thousands of applications, from your search bar to your next drug discovery. This is the stage where AI becomes a true utility, leading to Phase 4, the total transformation, where AI is as invisible and essential as the internet itself. And that pivot is everything. Because when it happens, the entire economic equation flips. The question is no longer, how fast can we train our next model? It becomes, what is our cost per answer for 1 billion users? The game shifts from a sprint for performance at any cost to a marathon of ruthless efficiency. And that shift, from raw power to ruthless efficiency, is the exact strategic opening that every single challenger we've discussed is built to exploit. That is the moment Nvidia's dominance will face its most profound test. So, how will we know when that test is truly beginning? If you want to evaluate whether these cracks are starting to form, here are the 4 key signals to monitor. First, watch the money. Is the AI CapEx spending from hyperscalers starting to slow down? Any major pullback could be a sign that the initial build-at-all-costs gold rush is maturing. Second, track the market share reports. Is the slice of the pie for custom chips and AMD GPUs actually growing in the data center? That's the clearest indicator of whether CUDA's moat is eroding and if other chips are finally good enough. Third, keep an eye on the code. Watch for major open source projects or popular AI models being built on frameworks other than CUDA. That's the ground level sign that the developer lock-in is weakening. And finally, look at what the chips are being used for. When you start hearing more about the massive and growing costs of inference rather than the eye-watering costs of training, you'll know the economic battlefield has officially shifted. This kind of thinking, tracking these metrics, is the core of understanding the business of tech, not just the products. And it's what we do every week in our newsletter, ARPU. If you enjoyed this breakdown of the strategy and the narratives behind the headlines, I think you'll get a lot out of it. The link is right at the top of the description. Thanks for watching.